Good afternoon, this is Schweitzer, and we're looking to investigate some more of our mathematics and possibly relate the non-mathematic, which was our last video on kinetic molecular theory, to types of containers. This is a good way of applying it and seeing how it all kind of works. So in this situation, relative to the kinetic molecular theory, how do these relationships fit? I have pressure, I have volume, and I have temperature. So how do these things kind of all go together? And can I use the kinetic molecular theory to describe these particular types of conditions? And let's get my pencil here, please. All right. There we go. All right, so in a rigid container, first of all, you should realize that the pressure, the volume is constant in this guy. Volume is constant. That should be fairly self-evident, seeing as the fact that it's not changing size. Here, maybe a little less, we mentioned it last time, but a little less obvious is that the pressure inside equals the pressure outside, or the balloon would be changing size. Therefore, the pressure in a balloon that's just static is constant. And although this is a piston, so this is allowed to move up and down, changing the volume, we don't have to hold our temperature constant, but for this one, typically, we're going to hold our temperature constant. Temperature constant. Okay? So now we want to compare each of the other two variables. What about pressure here versus temperature here? What about volume versus temperature? Okay? What about pressure versus volume? And we want to look at these in terms of kinetic molecular theory. No math. Okay? This could have been added to the end of the last slide, but it's a good review of all of our stuff we have here. Okay? So with that being said, we have the rigid container, which is the volume's constant. So if I increase my temperature, the particles just travel faster. As they travel faster, we get more collisions with the inside container of the wall, therefore we have greater pressure. This is a linear relationship, and it is described, any linear relationship would be described the same way mathematically. Okay, this guy, we have volume and temperature. So again, if I increase my temperature, particles travel faster, I get more collisions with the inside container of the wall, which means my pressure temporarily increases. The volume of the balloon expands due to that increased pressure. Also, a linear relationship. Now this one here, if I reduce my volume, now the fact that the temperature is constant would mean that the number of, or the speed of the particles is not changing at all. Okay, they're all traveling the same speed from start to end. So that's a kind of a trick question here. What's happening here? Well, we're not changing temperature, so molecular velocities, average kinetic energies, not changing. But what I do have here is less room. So as the volume goes down, there's less room, less area, so the pressure increases. We kind of talked about that before, that pressure is collisions per area, and we're reducing the interior wall size of wall area of the inside of the container. So this is our first reciprocal relationship. All of these should make sense. If I increase my pressure on this container, then the temperature should go up. If I decrease the volume, the temperature should go down. So all of these things kind of go ups and downs, and they should follow fairly intuitively. All right, so what do inverse and linear relationships mathematically look like? Well, we have a situation where x1 over y1 equals x2 over y2. This is your linear relationship. This is factor label. We have the inverse relationships. Inverse, sometimes I call it reciprocal relationships, where one goes up and the other one goes down, is x1, y1 equals x2, y2. And this is the case for like dilutions, and we've seen this stuff already before. Now let's combine these two, okay, into what we have on this slide. So these two are considered to be linear. Okay, linear and linear. That means that I would have this occurring here, which would be pressure P1 over T1 equals P2 over T2. And this guy would, the other one be V1 over T1 equals PV2 over T2. The last one here was a linear relationship, so a reverse reciprocal relationship. So this is what we got. We got pressure P1 V1 equals P2 V2. Now these guys all have names, all have individual names for these little relationships. We don't really care too much about them. If I don't use them for a while, I got to look them up. So those names aren't super important, but we can combine all these together. Now notice one thing we have here as we combine them. N is the number of particles. Number of particles actually in the container. Okay, not changing. That's constant. So we're not changing the number of particles. We have a balloon, or we have a box, or we got ourselves a piston, and we're not adding any particles to any of these containers. But we combine these all together, we get what we call the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. Okay? This is the combined gas law. Alright, so let's try it out, for example. So what do we need to know about a couple things before we actually use this thing? Okay, is we have our logistics here, okay, on this particular formula, okay, which is going to be P1 V1 over T1 equals P2 V2 over T2. What are some things we got to know about this particular formula really before we can use it? Okay. Now, for this situation, a few things. One, make sure your units, all your units, for whatever you use, has to be called absolute, which means they're based off 0. And the only one that really causes us issues here, okay, is going to be Celsius. Okay, everything else is fine. Celsius is not. This has to be in Kelvin. Okay, and you got to be consistent with the units across. Okay, so same pressure units, same volume units. Okay, so now again, mathematically, a couple things about the math. Really important. Again, some people are sharp with this. Some people are a little rusty. If I want to solve for my new variable, okay, really easy. Things move diagonally, and don't trap. Do not trap the variable you want on the bottom. If I want temperature T2, that's fine. Okay, so I can rearrange things. Also, very good chance, if a variable is constant, okay, then you can remove it. You can leave it in there, but it doesn't do anything. If the temperature is the same on both sides, well, then it just gets canceled out. If the pressure is the same on both sides, it gets canceled out. If the volume is constant, it gets canceled out. So you'll find that each of the each environment, whether it's this guy, the volume drops out. This guy, the pressure drops out. This guy doesn't have to, but the temperature could drop out. So in that situation, keep in mind there's a number of things where the variables can drop out. Alright, so here we have a rigid container, which means the volume is going to drop out. Or you can put it in if you want. It's just not going to change anything. So we want says this is that the temperature, the volume is 2 liters. You have 1 atmosphere, and we have 10 going to 20. Now, in this case, we're always looking for linear proportions. This is all of this stuff, whether it's any of these examples are just proportions. So the question is, if I double my temperature from 1 to 2 or 10 to 20, does this double? And the answer technically is yes. This does double. So this is an important question right here, trying to get you to realize that, okay, if I double my temperature, I double my pressure. But the problem here is that this isn't actually doubling my temperature. I'm going from 283 Kelvin. Remember, Celsius plus Kelvin equals Celsius plus 273 equals Kelvin. That's 283. This is 293. So really proportionally to the size of the numbers, I didn't increase very much. So let's run the math. Now, because using kinetic magnetic theory to describe what's happening. Okay, so the particles are traveling faster. There's more collisions with the inside container of the wall because they're traveling on the same area but faster. And the collisions are more forceful. Now let's do the pressure. So I got P1, V1, V1 over T1 equals P2, V2 over T2. And I'm looking to, first of all, I can put everything if I want, but I might rearrange this to solve for the new pressure. So move things diagonally, solve for this guy. It's going to be P1, this guy's going to move up here, this guy's going to move down there and leave this guy on top. P1, V1, T2 over T1, V2. Now you notice the volume is the same. P1 is 1. Temperature 1 is 283. And temperature 2, is located right here. So P1, V1, T2. Okay, that's 293, sorry. And then T1's in the bottom, 283. You could put the pressure, the volume if you want. 2 and 2 doesn't do anything for you. Alright, so you notice this is just a ratio percentage of the change in pressure. So 293 divided by 283, we should predict a higher pressure, and it should be, in this case, a little bit more than, obviously bigger. So this ratio really is 1.03, so just a little bit, times 1 is the atmosphere is 1.03. So this is going to be 1.03 atmospheres. Why am I using atmospheres here? Because I used atmospheres right here. Okay. So again, I just do the math and I get my answer. Okay. Just showing you this ratio really is what's controlling my answer here. Proportional temperatures here. All right, and there's my answer. Take a look. All right, the next one, a balloon. Okay, it's also going from 10 to 20. We should be realizing that this is not a doubling of my temperature. Okay, if I did actually double the Kelvin, then I would expect my container to increase to 4 liters. This one is not going to. We do have increased velocity, so we would expect more collisions to cause a temporary increase in pressure, which will make the balloon larger. So I'm looking for a volume increase here. Let's use this guy here to solve it out. And I'm going to solve for V2 this time. So P1, V1 over T1. This guy's going to go up here to T2. See, this algebra is super simple. P2 goes down, P2. And of course, the pressure's not changing. They're not giving you any new pressures because these are the same pressure. Put the 1 there if you want, but it may not matter. It will not matter. The volume is 2 liters. And my ratio of temperatures is 293 to 283. Once again, the same ratio is being multiplied by that, which is going to be 1.03. So 1.03 times 2 is 2.07, which we would expect from a very slight increase in temperature. Okay, next one we have here. Okay, a 2-liter container. Oh, there's my answer. Okay, there we go. Let's go to the next one. A piston has a volume of decrease of 0.5 liters. Okay, at a constant temperature using the principles of kinetic magnetic theory. Explain how the system changed. Well, we have less area, less room or area of the inside container wall. So even though the particle traveling the same speed, okay, same velocity, we have less area, which means increased collisions. Now the collisions are not more forceful, we just have more of them. Let's do our new calculate out. So we'd expect an increase in the pressure. And keep in mind, if I cut the volume in half, so 2 liters down to 1 liter, I'm actually cutting this in half, which would cause my pressure to go times 2. And if I do that again into 0.5, then I would expect my pressure to be cut volume in half again, the pressure once again times 2. So I went 2 down to 0.5, which means my volume decreased by 4 times. So I'd expect my pressure to increase 4 times. Let's try it. I'm going to take temperature out because temperature is maintained constant. This guy is going to move down below. So P1 V1 over V2. Notice the ratio of just the volumes here. Equals, okay, P1 is to V. Pressure 1 says a 2-liter container, volume, constant temperature. Okay, so let's call this, doesn't give the pressure here, sadly, I don't know why it wouldn't. Would be, let's go 1 atmosphere. Okay, so 1 times V1, which is 4 over 0.5, 2 is the original volume, and that gives me 4. 1 times 4, this is just 4 atmospheres. Okay, and again, that's just an idea of using the combined gas law. Okay, there's my answer for this guy. And this is our next one, but we're going to stop here for today, and we are going to pick up this new one. So we'll have a new slide here, and video here, slide, and a couple things that I might point out to you is we're now ended sort of our discussion of this combined gas law, P1 V1 over T1 equals P2 V2 over T2. Key idea here is that the moles are constant. So our next formula is going to talk about PV equals nRT. And what you notice about this one, it's got N in here, which is moles. So when you want to deal with something with moles, we move to this formula. And that's where we'll stop for today. Thank you very much.